We have 22 people on Zoom and 5 people on YouTube. Maybe we can start.
Okay. Shall we?
Good morning, good afternoon, everyone, and welcome to our February event with Terry. And Terry, this is all yours.
Thank you, Helen. This is a topic that I thoroughly enjoy. One of my favorite books of all time is a book called QED, The Strange Theory of Light and Matter. It was written by Richard Feynman, famous physicist. And the delightful thing about this book was he had a goal. And the goal was this. He wanted to explain to some of his friends how he understood physics, how he got his Nobel laureate, and he wanted to do it without using math. And his idea was that he didn't want to make people have to calculate the results. He wanted to show how the results came, how the calculations came from the logic. So it was an intriguing approach, and it was a difficult approach. It's not something you could do to just everything, but Feynman realized that he could, in this case, come up with some fairly straightforward representations that people could understand. Now, the actual calculations and getting those calculations to work efficiently and applying it to large problems, that's a much bigger issue. His point was simpler, saying that the basics, the operations from which everything emerges, have a simplicity to them that needs to be known, needs to be talked about. And that's what his goal was to do this. I've got 8 parts to this presentation. Originally, I was trying to very unrealistically try to cover the whole book quickly, but there's too much that needs to be covered on these basics. So I just went through the part where we get through the interference effects with soap bubbles, which is the first 1 or 2 sections of the book, which began itself as a series of lectures in New Zealand. So you can see the outline here, and who's Feynman, just get a little bit of background in case you're not already familiar with him. And his whole book is about photons and electrons. And what I'll be covering today is only about the photon part to give a realistic cover of that. Colors, the colors of bubbles. Remarkable amount of things covered by the color of bubbles. Feynman was notoriously irreverent. If you wanted Feynman to disrespect you, it was very easy. All you had to do is tell him, you need to respect me. And instantaneously, you would be at the bottom of his list of people he ever listened to again. This was just an inherent characteristic of Feynman, probably something to do with his background. He was raised, his family, his dad was a tailor. When he was young, he's considered himself an ordinary person who had unusual interest. He was not big on pomp, show, a number of other things, and he very nearly declined getting his Nobel laureate. And it wasn't that he was fine with fame. He had no problem at all on being entertaining and being known by people, but he just was uncertain about whether the Nobel Prize was that good of an idea. And in some ways, he even regretted it later because it redirected him away from his research. So you can get a copy of the original edition of Feynman Lectures, um, um, which are an amazing set of 3 books that cover just about every aspect of physics you can imagine. This was supposed to be an introductory course. It covered so much that to this day, people look at it for for far more than just freshman year of physics. It covers a lot. And there's always details. I love going through the lectures because I'll find things that I look at some paragraph and I say, I didn't realize he had said that. Or I didn't realize he had looked at it that way. Or I didn't realize he had that unique perspective that he puts on things for this particular problem. So lots of little goodies and finds in there, and a very good set of books that are online. You can get them in their entirety online without any charge. So that's great. He's had some books that have been written about him. Famous one is a particularly famous one, Surely You're Joking, Mr. Feynman, which again captures his irreverence very nicely. There's one joke. He went on a long road trip with a well-known physicist whose name I admit I forget at the moment. And their own descriptions of their own trip were just strikingly different because the other fellow was saying it was so great to go with this great mind. And Feynman was just, it was talking about amusing little anecdotes from the past. He did not consider what he had said to be that irrelevant. He actually made a joke about his own QED theory in front of a bunch of Princeton mathematicians, and he played his own theory for a laugh. He said, "Yeah, it's probably all wrong. Probably something like checkers." And he just, but how many Nobel laureates do you know who would make fun of their own work in front of a crowd of mathematicians to get a laugh? And he meant it. And he just said, "Yeah, it's probably wrong." Said his point was the details of what I calculated, those are right, but we still don't understand what's really going on. The particular theory that he got a Nobel Prize for is called quantum electrodynamics. Big name, nicely abbreviated to QED, nothing to do with the mathematical use of the word QED, but it is a way, in a nutshell, of describing electrons and photons, particles of light, the particles that we most often encounter in nature because we don't see the nuclei of atoms, we just see the electrons. So those two particles cover a lot of turf. QED itself is an example of what's called a quantum field theory. And there's a marvelous irony in this because the premise that Feynman started with was that everything was particles. You hear about the particle field duality, the particle wave duality. Feynman had a very unusual take on this, and a lot of times this people don't point this out, but it's worth pointing out. He started from the other end. He said, "What if it's all particles? What if it's just particles?" And we don't really have a field. Now, at the same time, he had no problem embracing field theory. He had no problem working with fields. He used them in the math. He was extremely pragmatic about that. But when he was trying to poke at something and say, what's really, 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 really going on at the deepest level, then he would back off. He would say, let's see if we can make it even simpler. Let's just dispense with the fields and have just the particles. And was a pretty radical concept. In fact, it was so radical, most of his fellow physicists did not understand it at all at the time. You can get on the Internet Archive, marvelous things that are no longer under copyright. You can get copies of this. So his first edition, which has this beautiful picture that you see over here on the right of oil film, same kind of colors you see in a soap bubble. So that's on the cover of that book. So a good resource that you can find. There are versions of it you can buy on any number of sources. If you get those that have more recent intros. This one has the original intros and the original preface. Photons, particles of light. Why do we think that light is a particle? Because our technology tells us it's a particle. You can go in to a device like a photomultiplier, something invented back in the 1900s. You can have one photon, one tiny little bit of light goes into it. This causes an avalanche type reaction, which the one photon releases a couple of electrons. The electrons release more electrons, and back and forth it goes. So you see it just crawling up through here. At the end of that, in Feynman's time, they would have had, which is back in the 50s and 60s, this would have been sent to a speaker. So you would hear a pulse, you'd hear like a little snap, so that you just got a photon. So it is a remarkable thing that when you make the light very dim, you can't get away from this effect. You just keep winding up and saying like, oh, I below a certain point, there's just nothing. And up to that point, I get a number of photons that is remarkably just proportional to the energy that you're putting into it. So that it's like the energy kind of gets grabbed into a little bundle and then it pops out. You can see these things directly these days. You can go out and buy equipment right now. You can go on the internet right now and find some devices where you can watch this yourself. This is an actual little picture of a amplified light picture of a raccoon in the dark. That's under very dim light. But if you go even less with the same device, what happens eventually is you get this little sparkly effect. You start seeing little bright points of light. You see the little ears, see the little raccoon ears there? That is actually light images coming from this guy. So the photons are so few and so far in between that you can just barely get that. The technology is essentially the same as what Feynman described. This device was not available at that time, but these little channels just have those same little avalanches of electrons going back and forth and back and forth. And then instead of hitting an audio connection, they wind up on a photo connection. They produce a little flash of light. So same technology, but it's been turned into night vision goggles, and very useful technology to have. And one, it's commercially available, so you can find it out there. But it's just remarkable because if you want to do this experiment, you can do it at home. Even human eyes, this has been found out statistically, we can see photons. We can't see them well, and they're kind of like the subconscious level. We can't quite get them to where you say, oh, yeah, that's exactly where it was. But if you do a statistical analysis of people in extremely dim light, it turns out humans do statistically detect photons. We can say, yeah, there was one right then. There was another one then. So even human eyes, when they're trained for it and we've been in the dark for a while, we can potentially see these little flashes. Photons, light always comes in flashes. And isn't that remarkable? Because we don't think of like that. I know everybody hears the word photons, but to imagine lights as being these little particles takes some stretches, and that's what we'll be getting into in this. The interesting thing about photon, again, I'm not sure why this isn't emphasized more because I think it's just fascinating. The idea that photons are particles, period, did not come from Feynman. It came from a fellow named Einstein. And not only did it come from Einstein, it's the only thing he ever got a Nobel Prize for. And considering he could easily have gotten about 5 Nobel Prizes, you have to go down the list, right? Special relativity, general relativity, his work on the existence of particles, the bouncing of particles around. He had a number of insights that he easily could have gotten a Nobel Prize for. The one that he got one for was about photons being particles. And Einstein was hard-nosed about this. If you read this quote here, light seems better modeled by assuming that its energy is not, now look at that, is not spread continuously over large volumes, but consists of finite number of energy quanta that are spatially localized. It means they're one little tiny spot. He uses the word point. They move without dividing and are absorbed and generated only as whole units. People often say Planck is the one who came up with this. Planck dodged this until years after Einstein brought it up. Planck did not want to go this route. Planck was very conservative, and he was a brilliant man, but he had to be forced screaming and hollering to get to the point of coming up with the idea of Planck's constant. He never used the term of photon units. He didn't even use the equation that we usually associate with that. That came later. So the real force of saying that photons are particles came from Einstein. And Feynman picked up on that. He said, hey, I'm good with that. I'm going to follow that idea and see where it goes. Einstein's eye did not play well. This is characteristic of the people who get Nobel Prizes. It does not mean that people love what they say when they come out with it. So when he came up with this idea, people just looked at it and said, that's ridiculous. That is absolutely absurd. We know that light is a wave. It can't be photons. And you're point blank saying it's a little particle traveling through space. So even the Nobel announcement refused to talk about photon quanta. Instead, they talked about the photoelectric effect, which was kind of a weasel word saying a way of saying, yeah, he found something very important here. The equations all work. It's extremely predictive, which is important, which is why he got the Nobel Prize for it. It's extremely predictive. Math works out right. But the way he phrases it, we're not so sure about that. So because they just couldn't conceive that that was a real thing. And there are good reasons for that confusion because to this day, wave-particle duality remains the most baffling feature of quantum mechanics. People can tell you they've got it worked out, they've got this, they got that. It is baffling. It is still baffling. It has never ceased to be baffling. So, and Einstein was aware of that. He knew that, but he said, we got to look at what's happening with this quantization if we want to understand it. Now, if you have ever, uh, this is the emphasis that sometimes physics gets dressed up too complicated of a fashion. If you have ever dug a hole, you have noticed that in the process of digging a hole, you wind up with a pile. So we have a pile, we have a hole. If you can understand the ideas of digging holes and making piles, you understand the phenomenon called interference. Because all interference is the mathematics of digging holes and making piles. And you can dress it up in all sorts of fancy ways, but that's really all it adds up to. If you look in the leftmost box here, wave cancellation, imagine two things. You got a wave, two waves heading towards each other. One of them, it's up on the left and down on the right. The other one's down on the left and up on the right. What do you get? They cancel each other out. This is just like filling in holes. The up on the left side fills the hole on the left side and vice versa. And you wind up with a smooth thing. That's called destructive interference. It means the waves cancel each other out. Now, the other thing that can happen is you got two piles that pile up on the top of each other. So you wind up digging the hole deeper and you wind up making the pile higher. The same thing happens with light. That's, in fact, with any kind of wave phenomenon. It's the same idea. It's just more dynamic. You know, your piles kind of stay there for a while. So it's easier to visualize it when you're doing piles and holes. But it's the same idea. It's just working. The piles are a lot faster and they change a lot more quickly, but it's still the same idea. So when you shine a light through two, and I'm simplifying some details here. This would be a monochromatic source if you want to be particular about it. But if you take a source of light and you run it through two slits, everybody's heard that one, right? The two-slit experiment. Well, it works with photons. But in photons, it's been known for centuries. So people knew that if you do this, if you put it through two holes, you wind up with this marvelous little pattern on the far side. And by the way, this experiment is a lot harder to do than you might think. There's some good YouTubes out there on how to do it, but it is trickier to do. But it also has been done and has been known for a very long time. This is one of the reasons why people said, what is this? What is this particle stuff? What? What are you talking about, Einstein? What's wrong with you? And yeah, again, they eventually came around, but that was not the reaction they gave them at first. This is something I'm just going to mention in passing because it does make a difference. When you look at that and you say, well, two waves cancel out and you get nothing. And if you know anything about energy conservation, your brain should be saying, wait a minute, that doesn't sound right. Because you can't cancel out to nothing. If you add them together, you can say, oh, yeah, I just added the energy, but waves have energy. So what happened to the energy? And that's actually a very good question. And it's one that you need to look at carefully. When I encountered this, I went on the internet and I looked for something about that. And I found this quote by some guy named Terry Bollinger. I literally had forgotten my own quote on this. So this was just something in the Stack Exchange. But the point is, even if I'd forgotten my own point, the point's very simple. When you make a cancellation area in optics, what you've really done is create a mirror. You're making a region in which you can't dig holes anymore. So you get your little hole diggers come along in there and say, I want to dig a hole here. And there's this fence that says, you may not dig holes in this area. We are a forbidden area. We do not allow hole digging or pile pushing. You must go somewhere else. And you go, all right. So the hole digger bounces off and goes in another direction. That's pretty much what happens with all sorts of phenomena. If you look at a peacock feather with those beautiful colors in a peacock feather, that's exactly what's happening. Is the peacock feathers create a little region where it essentially has a sign in front that says, no holes allowed for this frequency of light. So the blue light just bounces right off, or the red light, or whichever area it is, whichever it is that they have forbidden. So it's an interesting way to think about this cancellation is that any phenomenon that looks like a mirror has some variation of this cancellation effect. It's forbidding the entry of photons into that area. Feynman's starting point was exactly that. He took Einstein's viewpoint. He said, I'm going to take it at face value. I'm going to look at particles only and see if it works. To the best of my knowledge, no one had done this before. And the fact that Feynman did this and at the same time fully acknowledged all of the behaviors of light, there's an easy thing to do in research, which is this. You look at an idea and you say, this is important. Particles, photons are particles. So far, so good. The trouble is, if you then go on to the next step, so you start you start saying things like this. So everything where it doesn't look like a particle must be bad experimentation. And as soon as you go down that path, you're in trouble because it doesn't work that way. You got to look at the full set of experiments and say, what does it all do? Feynman was good at two things. He took an adamant viewpoint and said, these things are particles. But he also said, and every single blooming behavior we see is exactly what we see. So when you see the interference, it's the interference. There's never been any deviation from that. When you take an individual photon, it still does it. So he said, take them both seriously. So this is what Feynman did that no one had done before. He took this idea of saying that, well, they are particles, as Einstein said, but something strange is going on here, produce these new behaviors. Einstein refused to add devices. Now, if you look at something called pilot wave theory, this is the idea that de Broglie originally came up with. He broke it up in two parts. And most of the Copenhagen version of quantum mechanics also breaks it up in two parts. You got a wave, you got a particle, and then you have either some mix of the two. They either alternate, or they, in the case of pilot waves, they actually are at the same time. Feynman refused to do that. He said, no, it's got to be one or the other. And he chose the particles. So in doing so, he avoided the concept of fields. And this got one of his co-winners of the Nobel Prize a little miffed at him because um, uh, not everybody agreed with the idea that there were no fields. So Feynman took an interesting perspective with that. What happened when he did that, when he simplified as much as he could and said particles, 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 and eventually he dropped even atoms, he just said electrons, photons, forget about everything else, is he wound up getting better math. The math that he wound up with could predict things that nobody else predict. And that's because of the simplicity. There's not a coincidence here. He went for maximum simplicity, but taking everything into account and said, what model takes all that simplicity and then builds it into something new? And this is what he did. So he came up with this QED model that turned out, to his own surprise. There are recorded statements of him saying, like, I didn't think that would work. So he was just like, I thought it was a good idea, but I didn't really think it would work that well. But it did, and it started predicting things that then the experimentation started predicting out to like 6, 7, 8, 9 decimal places. So he was onto something, and it took a little while for that to be fully realized. So what was Feynman looking at? Because what was the logic behind how does he explain a particle that at the same time does all the optical things that you see? And one of the paths for doing that, which apparently is one of the ones that inspired him in some of this, is mystery of partial reflection. What's partial reflection? If you've had no glare sunglasses, you know this. You have the old pair of glasses and they just glare something terrible. And then you got these newfangled, that's how old I am. The newfangled, quote unquote, because I'm back from the era where my original pairs of glasses didn't do this. The new ones, you can see the person's eyes better, and the person inside sees a lot less glare from the outside world. That's a marvelous little technology. And to do that requires a deeper understanding of light. Turns out the same phenomenon is very closely connected to the effect that causes shimmering colors when you have a little bit of oil on top of water. It causes very similar shimmering colors from soap bubbles, essentially the same effect, just in a slightly different form. So you have these examples of what's called partial reflection. And they have versions where you have different colors popping up. Most of your no glare sunglasses, you'll see that you can see the little bit of green in this example. This guy's got a little bit of green on his glasses. So what is the key characteristic that causes this to happen? And why is it important? And I love this because that seems like such a simple question. Okay, what makes these things happen? And what's the key thing I have to make those things happen? And it turns out to be nothing more than two reflective surfaces close to each other. That's pretty simple. There's not a whole lot to that. But what's going on with this? This has been known for since at least Newton's time and longer, that glass has these odd characteristics on how it reflects light. And the characteristics have to do with how thick the glass is. So if you have glass of a certain thickness and you send some photons at it, you get what's called partial reflection. You get photons that come back, small number in most cases. Then you have photons that just go on through. In the time of Newton, it's fascinating because Isaac Newton tried to understand this phenomenon. He knew that something strange was going on with this. He was going like, this is definitely weird. And he loved optics, so he was trying to find out what as much as he could about how this phenomenon, how this worked. He discountenanced, he discarded one theory, which was that there are little holes in light, so that most of the light goes through the holes. There's occasionally little spots where those spots reflect it, and that's where you get the partial reflection. If you go through the full argument, and Feynman covers this in his book nicely, Newton was able to eliminate by saying that, no, because I can polish glass, I can make it arbitrarily smooth. I can get rid of whatever these little interfering things are. It can't be that simple. And there's other reasons why Newton realized it can't be that simple. So what are the characteristics? What makes it reflect sometimes and not, and what are the numbers? Selection could not be a surface-only effect, was what Newton realized, and it came up later. There had to be some connection with the actual structure of the glass itself. And for Newton to be asking these questions, and this is, again, we have our little mysteries, and sometimes we just don't have the mechanisms to answer that. Newton was asking questions about quantum mechanics centuries before quantum mechanics existed. He was saying, like, I know that this is not just a simple surface phenomenon. I know that there's something very interesting going on. I can characterize some of the features of that, but he couldn't come up with any broad mechanism to come up with an explanation. And even to this day, Newton was stuck on that point, and we're still stuck in a way because we still do probabilities, not certainties. It's one of the classic complaints about quantum mechanics is that when you go down to this level, you wind up with probabilities, but you just never get these absolutes that you have in classical physics. Feynman's particle-based approach, again, taken from Einstein. Here's an important initial qualifier. When we go at a problem like this, and when Feynman went at a problem like this, you need to know your own assumptions, and you need to know them very well, because it's so easy to sort of gloss over something and realize you were actually thinking something a little bit different. Feynman's independence assumption was this: every photon determines its own path. Why would he say that? Why would he think that? The reason he would think that is because experimentation backs it up. Feynman was adamant about following experimentation. What does the experiment show you? And what experimentation shows you is that if you dim a light that's going to a surface that has this effect of partial reflection, and you do the experiment, and instead of putting a gazillion photons all at once in a laser pulse, or a weak wave where it's still just a wave, it says, what if you just keep thinning it down until finally you're just getting like one particle, one photon, for some ridiculously long period of time, maybe even a year? No reason why not. One photon per year, twink, goes to the little reflecting surface, bounces back up, and you record the results. Did the photon bounce? Did the photon go through? Did the photon follow a certain path? Here's what experimentation says. It doesn't matter. One photon, a trillion photons, some unbelievable number of photons, they all follow the same rules. The single photon has all the ability to figure out that path and figure out the probabilities on its own as some enormous mass of us. What does that mean? It means that if you talk about interference, you don't have to think about a whole bunch of photons interfering with each other. You have to focus on that one photon. You have to figure out what is that one photon doing And how is it doing it? And that leads you down a very interesting path. So this assumption is something that's very well validated experimentally, but it's easy to not recognize it because it's just so counterintuitive. I'll give an example, a more extreme example. We have Einstein lenses that are millions of light years across. And according to this principle, one photon on the other side of the universe, literally, can go through that lens, can go through that gravitational lens, through the entire lens, and come over this side and give a single focus on a telescope here at Earth. And it's all exactly the same as if it had been an intense pulse that was bright enough to see across the entire galaxy. So think about that. How does one photon know the same math exactly as some enormous burst that would illuminate the entire set of galaxies? So that's how strange this gets. But experimentally, including with lenses like that, that's what we always see. Individual photons have the whole story. If you can understand the photon, you can understand the underlying physics. That's remarkable. That's why Feynman was able to simplify things. One photon reflects from multiple locations. That's why I was saying about these surfaces. So you have two surfaces. This is the key insight. If you want to understand these partial reflections, if you want to understand these colors, you have to recognize that the photon is bouncing off of two pieces of light. So the partial reflection is amplified or turned off, one or the other, by the presence of the additional surface. Now, if light is a particle, can you see that there's a problem here? There's a problem here. There's a really interesting problem here. Your eyeglasses, if you have eyeglasses that have anti-glare on them, those anti-glare coatings are messing with time. And I don't mean in a figurative sense. I mean in a quite literal sense that without ambiguity of time, your anti-glare would not anti-glare. It would not be able to stop the photon from doing that. The photon, if it's a particle, has to see both of those surfaces. And this is where Feynman refused to back off. He said, I'm still going to stick with particles, but I'm going to look at the particles in terms of saying they can do things that bend our usual definitions of how particles travel. He's saying that in some sense, in some way, and he intentionally said, I don't, he said, this is, you got to follow the algorithms. He's not trying to explain it. He's saying, this is how you calculate it. And the calculation is that you show the photon going to both surfaces. So this is a non-classical concept. You can't do this with a baseball. You can't have a baseball bounce off of two surfaces and then come back and interact with itself. This is so strange that I want to point this out. If you had a no glare, most of the no glare layers are obviously extremely thin on your sunglasses, on your glasses. But you can make them thick. And you have to be much more precise when you do this, by the way. This is not an easy thing to do, but it absolutely is doable and has been done many times, is that you can have a length like an entire foot, which conveniently is almost exactly 1 nanosecond of light travel time. It'll actually be a little slower on the glass. But you can have that 1 foot, and you can have the same interference effect so that photons are guaranteed not to glare, that they'll go through the entire thing with 100% certainty. The only way you can calculate that is to assume that the photon is lost in time for about 2 nanoseconds. What do I mean by lost in time? You can't have the non-reflection effect until that 2 nanoseconds is up. If you try to look at things at 1 nanosecond or at a fraction of a nanosecond or some earlier time, if you have a particle that you could, photons are hard to detect, but if you had something like an electron doing the same thing, which you can, and you said, no, I'm gonna cheat. I'm gonna look early and say, where's it at? You'll find out the effect disappears. So you have to let the entire 2 nanoseconds go by before you get the interference effect. So this is not your usual concept in classical work of how particles work. And the beauty of the Feynman diagrams, he said, if I'm going to assume it's a particle, but I'm also going to allow that particle to do different pathways, to do different things, and then add this all together. So it was a marvelous insight he had, but required bending our usual definitions of time. I am amused sometimes when I see articles that talk about quantum results have shown that ambiguity across time, and it amuses me because that's always been there. And this is a good example right here. Just to do anti-glare requires an ambiguity in time for the quantum mechanics to work. This is similar to the spatial ambiguity. It's just working in the time domain. It's everywhere. It's not uncommon. You don't have to have a whole new experiment to get ambiguity in time, because many of these self-interfering, anytime you use the word self-interference, you're playing with time, space, or both. It's not the very fact it's interfering with itself means it's seeing different versions of itself at different locations and at different times. Using experiments to find patterns. We've got this interference effect. It's really interesting. What does that say about reality? Can you find something deeper about that? If you map this out, this is the importance of experimentation. You say, well, okay, I want to see if I can't figure out how this works and it doesn't make any sense classically, can I at least characterize what are the critical circumstances? And yes, you can. And what you find out is probably even stranger. It's that you have, as you increase the thickness of the glass, you start changing the amount of reflection. It goes up to a maximum, in this case of about 16%, and it goes down to a minimum of 0, the no glare case. That's the one that they shoot for with your eyeglasses, or it's more complicated because you have many frequencies there. So yeah, you go like, how? What? How does this work? Because and by the way, Newton was aware of this stuff, and he was like, I don't know, he couldn't explain it, but it didn't keep him from noting it and saying this is extremely interesting what's going on. So what is going on? So Feynman used this kind of data to say, okay, I'm going to stick to the particle model, stick to the particle, Einstein's particle model, and see what I can do. And what he found was that there's a little arrow associated with this. The arrow, you have to represent the probability as an arrow. And actually, as it turns out, the arrow is the square root of whatever that probability is. So if you have 0.4%, you have a 0.04, a 4% probability of the photon reflecting. Feynman said, how do I take care of this? I'm going to draw a little arrow. And he even jokes about it, says, so this is really profound, folks. I'm going to draw little arrows on a piece of paper. That's how I'm going to solve this problem. But his point was serious. He was saying that, yeah, there's a lot of math you can associate with this. Feynman had no problem going very deep in the math to do this as a workable problem to give actual probabilities. But he would not back off from the fact that the actual mechanism is nothing more than drawing little arrows on a piece of paper. Now, the arrows have one property. They can never be longer than 1. 1 is the maximum length of these arrows. 1 represents 100% probability. Then you go down to 0, which represents 0 probability. In between, you use a square root. So it's not directly proportional. I even did it when I first copied these slides. I even made that mistake. It's so easy to fall in that error. The length, this arrow he draws, is not the same thing as a probability. It is the square root of the probability. So for a 0.04, 4%, you get a much higher length for this arrow, a much longer length for this arrow, which is 0.2. So 0.2 out of always a maximum length of 1. So he found that allowed him to start representing all these probabilities using little arrows, and the arrows have direction. So you have different angles that they can go at. So he started coming up with these little squares, and the square gives you a probability. The total sum of all of these probabilities for any given photon is always going to be 1. So essentially, he's breaking it up into these little areas. The areas all add to 1, but the lengths of the arrows don't necessarily add up to 1. You have different combinations, but you always have this relationship. So I have this nice, nice simplicity in how that goes. Feynman added another rule to these little arrows. Remember I said that there were 2 different things going on with that photon going through the glass. You have the first reflection on the first surface, and you have the second reflection on the second surface. What Feynman said was, well, each of those has one of these probabilities attached to it, which you can actually measure. So there's a probability of the photon reflecting from the bottom. There's a probability of the photon reflecting from the top. So he would add those and come up with a final arrow. So the arrow would then say, okay, if I add this one this way and that way, and these are arrows, these are not just sums, these are actual directions. What is the direction of the final arrow? And then from that, I can get a final probability. So this is an oddly simple way of doing math. He's just saying, take the arrows, arrows have direction, square the arrow, you get the probability, or take the square root of probability and you get the arrow. Either way, you go back and forth between these two. But when you put them into the arrow form and you start stringing these things together, you just add one, and the additions, there's all sorts of nice mathematical ways of doing this. But the simple way graphically is just this. You just shuffle the arrows around, put the X over here, put the Y over here. This would be the reflection from the first surface, the X. The Y would be the reflection from the back surface, go over here. And then you wind up with this final arrow. So now, if you're looking at this, the other questions you should be asking, you need to be asking is that what's determining the direction of these arrows? Because a probability is just a number. It has no direction to it. So where are all these directions coming from? And that was the part, well, first point out, you can keep doing this. It's not just a one-time thing. This is, you can, you can have a whole bunch of these arrows. And you can have an event if you're going through, like, for instance, diffraction grading. If you're going through layers, you know how when you take out some mylar wrap, how it looks shiny, it looks like a mirror. That's what's going on there. Each one of those little layers of that wrapping is adding its own little arrow. And by the time you get done with it, you can wind up with a pretty good mirror. You can wind up with something that reflect light quite well. That's what this kind of arrow, this kind of situation represents. You have like first layer 1, second layer 2, third layer 3, 4, 5, on it goes. So these would be different thicknesses of layers. So you have this nice little addition of property, but you always wind up with just one final arrow. And what does that mean? It means you always wind up with one final probability. How likely is it for light to be reflected? Now, slight tangent, but this, whoops, went too far. Not so much a tangent, but just to explain this point a little bit. Feynman notes that there's an additional rule, and this has to do with materials, and it's not something he gets into, and it's not something you need to know the details of. But it's very important for understanding the actual examples of thin films, such as in your no glare glasses, that one of these arrows gets reversed. So he just starts out and says, I've got an incoming photon. It doesn't matter where you point that photon's arrow. You can point it any way you want to. That's the arbitrary nature of the phase, what they call the phase. But once you set it, you have to keep with it. You have to say, okay, I set my arrow at 3 o'clock and I have to stick with it. And then I have to start altering that 3 o'clock according to certain rules. And the first rule is that when you reflect from the front surface, you reverse the direction of the arrow as well as reducing the length of it. Now, I've intentionally used 0.5 here instead of 0.2 just because it works out a little easier graphically. It's kind of hard to squish it down there to the 0.2, but it's the same idea. So Feynman's point, and he mentions it in all these slides, is that the first one goes backwards, and then the second one, when you reflect from the back surface, because you're going from a denser medium into a lighter medium, it turns out that the photon level, that keeps the phase. So you get the same phase as the original, the same direction as the original arrow that came in. So that arrow points this way. Okay, well, now look at this. If I take this arrow, the green one, and I stick it over here, so I go green goes this way, and then it's better if we do this. The blue goes this way, and then I stick the green arrow onto the other way. It doesn't matter which order you do it in this case. You come out with 0. There's no vector. They cancel each other out. So what this is saying, if you add this rule that Feynman talks about shortly after figure 9, is that for an atomically thin film, even if it's a highly reflective material, you don't get a reflection. You don't get much of a reflection. Why? Because the arrows that you get reversed here and the other way here are so close together that they wind up canceling. Have you ever looked at a piece of uh, the very thin layers, very thin films of gold? You get this effect. You actually can see through them. And this is part of why you can do that. So even a highly reflective material like gold will be able to, will lose its ability to reflect photons if you make it extremely thin. Then gold leaf is fun stuff because it's so malleable that you can just squash it to layers so thin that you actually start seeing this quantum effect kicking in. Stopwatches. How do those arrows make their different changes? I gave you one example of how an arrow changes, which is that if you reflect off a front surface from a lower density optical medium to a higher density, you get a reversal. Okay, so that's one change. That's just a reversal. How do they work in general, though? Well, it turns out that what you need in this case, and again, Feynman is intentionally humorous about this, you need a stopwatch. That's the advanced mathematics that you need to understand this is a stopwatch. You need a dial that rotates. that's 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 it. You don't need all sorts of fancy equations, integrals. You get the integrals later, but to understand the basics, you just need a stopwatch. You just need a little stopwatch that moves and changes as the photon moves through space. So straightforward idea. So we got two transformations on the stopwatch. Reflection will either keep the direction of the dial the same, or it will reverse the direction if it's on the front surface. Same effect either case. But when you are moving through space, it simply turns the dial. And the dial turns at different rates for different frequencies of light. Feynman talks about this in his lectures. I like the audio. The audio version often has little tidbits that you don't get in the printed version. Feinstein was incredibly careful in his statements, and often he said things that even the editors of his lectures didn't always quite catch what he was trying to say, and they would misunderstand it a little bit. So it's often good to listen to the audio versions of his lectures, and these are available. So you can see that Feynman defines the concept of energy in three ways. You can have energy in the classical sense. Photon is pure energy. It has no rest mass or anything. But you also have mass as measured by inertia because a photon does have gravitational mass. So that's another way of measuring the mass, the energy of a photon. This is a good old E equals mc squared, nothing more than that. But the one that people miss, the one that's very easy to miss, is that there's another definition of mass, which is just frequency. Some people would call this the quantum frequency. Feynman calls it the frequency of amplitude, that little arrow we've been drawing, the little arrow that goes out. So the faster that moves, the bigger the mass. How's that for a complicated relationship? So you sitting where you are, you have an amplitude. You have a frequency. It is unbelievably high because you are a combined mass of a whole bunch of things, and there's a frequency associated with that combined mass that is independent of the individual frequencies. And it's hard to measure, very hard to measure for large objects, but not impossible. People can get almost up to dust-sized particle ranges these days on measuring this special frequency. It shows up in double slit experiments. So three ways of defining mass and energy. Mass energy, same thing, equals mc squared, but also the quantum frequency that shows up even in soap bubbles. So stopwatch is the total energy of the photon. So guess what? Blue light has a faster stopwatch than red light, about twice as fast. As it goes through space, you get the same, they're both winding out at different rates. So matter particles also have the same thing. The total energy of the particle for an electron is also a frequency, and the frequency works the same way. It interferes in the same way. It follows the same rules of interference. There's a catch with an electron, though. And the catch is this. The electron, unlike the photon, has something called rest mass. And what it means is that you cannot there's no way you can get rid of this inherent uh, uh, frequency that goes all that's attached to that particle. If you have an electron, You
All
haven't.
right.
Is someone trying to say something? If you have this inherent frequency, if you have this rest mass, you have this inherent frequency, you can't get away with it. Now, if you look in physics literature and you see things like imaginary exponentials and some complicated math, it doesn't mean that those are not trivial. There's a lot of interesting things that goes on with that. But as it turns out, imaginary exponentials, which look really wild and say like, oh, this is a concept I'll never understand. Yes, you can understand it. It's just a stopwatch. It's a way of expressing the stopwatch. In many ways, the stopwatch is even a little more accurate because the stopwatch has no difference about direction. It's completely even all the way around. Whereas imaginary exponentials, you do have some structure to it that's actually a little bit redundant. So don't let the terminology throw you off sometimes. Simple things are often beneath these other ideas. And the idea that mass energy is a frequency is an extremely helpful idea for understanding any version of quantum mechanics. You may express it in complicated ways, but you don't have to have that full understanding to get the concept down. So why do you get a small reflection in many cases? If you've got a very thin glass, you get that cancellation effect. I've already talked about this. This is one where I gave a more extreme example. If it's atomically thin, this will go pretty much to zero. So you get almost no reflection. That's why gold foil works. You can see this marvelous little ability for the gold to actually transmit light because it's so thin. And there's a connection there. Gold is extremely reflective. It's one of the most reflective media that exists. And yet, if you can put it into a thin enough sheet, you can actually see through it. The way you get your final probabilities then, this goes back to that issue I said earlier. So yeah, you got these arrows, and the arrows are just the square root of probabilities, but where in the heck do the arrows come from? Well, they come from two things. You get reversals due to reflection, and you just get rotation because it's going through space. It's traveling, zipping on through there. So you want to calculate how fast it's going to turn for a certain length. And different photons are going to have different amounts of rotation as they go through a film. The maximum reflection recurs when you get these half turns because then they add up when you get the reflection back in that way. That's where you get the 16%. So if you have that case, you have the arrow that originally that you get on the back surface matches the arrow in the front surface that's coming in. And then you have your reversed arrow that is half out of phase, so half out of reverse, and you flip it again by another half, you wind up the same direction. So you're undoing the damage done by the front reflection. The front reflection always reverses it, but if you have exactly one half of a turn, they cancel and it goes to a maximum. And suddenly you get a much bigger glare. You get a worse glare. This is your worst case scenario for glasses. This is what you don't want to do. Sebastian, did you have a question?
Yeah, just one remarks maybe because you shouldn't. Maybe it will change uh, your talk, but please do not use probability as this square root of, because it's not the same. Square root of probability it means that you have real value from 0 to 1, but in that you have vector and you have you can take one direction and other direction, which is plus and minus thinking. So for this you can have more values than just 0 to 1.
Yes,
So
I agree completely with that. And I
if we
only
can
want to, I
if we can not use probability as the main thing here, because the main difference is that this is not probability and square. This is even not square of probability.
No, it is not. Agree completely. And the point was that when Feynman was using the amplitudes are what is fundamental. So the idea that you get the probability, that the length of the amplitude has a relationship to the probability is the point. Starting from experiment, you get a probability, or you get a percentage. not how many of the photons get reflected. So Feynman's whole point is that the amplitude is far more fundamental than that, and you cannot understand how these things behave looking only at the probabilities. You've stripped away the structure when you get to the probability stage. So I agree completely. So maximum reflections occur at half turns. You can also cancel reflection completely. In this case, you want to have the thing, well, the simplest case is if you have an atomically thin film, then you get a full cancellation because you have that reversal. So you have the reversal at the front, you get the little switch here where it goes, it alters the direction of the amplitude. You get the back direction where it goes this way. And they cancel out to 0, which is the example I already showed. I'll go back very briefly just to show that again. That's what this is. So for an amplitude where you have an amplitude of 0.5 in length, which is a 1 in 4 chance of a photon getting through, then you get a complete reversal and you wind up with no photon. So that's exactly what this one is talking about. Now notice that there are angles that are involved with all of this. So you've got excuse me. You've got angles with the arrows, and the way you add these arrows, because you just adding them end to end, you wind up with things like Pythagorean theorem and how these things add together. So simple form math, Pythagorean theorem is a particularly interesting case of where these things add together with this. Colors of bubbles. Why are those bubbles colored? Well, part of the reason is because you have this cycling effect. You have these amplitudes that are rotating at different rates. So you go through here and you can see how this probability of a photon reflecting is increasing. And again, this is just a scalar. If you want the real structure, if you want to understand what's going on, you have to go to this amplitude. There's no, you can't, as Sebastian said, you can't just take a square root of probability. That doesn't tell you the story. You have to look at these rotating vectors, a much more interesting and structured concept than just having the probability. But what happens is as these amplitudes diverge with thicker and thicker layers, see this cycle? You're going through, you start with almost 0, then it gets a little bit larger. Again, the square represents a probability. Square represents probability, and then it shrinks back down to 0. Well, doesn't that sound familiar? Yes, that's the 0 to 16%. So this idea of using amplitude arrows that rotate as they go through space gives you an explanation for why you were seeing those cycles, the same cycles that baffled Isaac Newton. And maybe even more importantly, I say it is more importantly, different colors have different speeds of rotation of the amplitude. This corresponds pretty much 1-for-1 with what we think of as the frequency of the light. So blue has about twice the frequency of red. I'm actually more of green, so you get about twice. So you get the blue winds up rotating faster as it goes through that film. And as a result, there are different levels where it peaks. So you have the blue peaking here, you have the red peaking here, and guess what? You get kind of, and I don't know for sure if you can see the arrow I'm pointing, but this peak gives you something like this, a purplish color, because you're getting red and blue that are combining together with that. Obviously, we've got some green in there too to throw some more confusion in, but you keep getting these different peaks. So for different thicknesses of the bubble, you can actually wind up with repeats. You can see the same color playing over and over again as the bubble gets thinner. If you've ever seen a bubble that is kind of resting, this one shows it a little bit. There's a little bit of gravitational pull, and there's a little bit of layering of the colors on this. So these bubbles will often, vertical bubbles, will show this kind of different levels of peaks. So you can actually watch the different peaks where the red and the blue are reaching their maximum probability of reflection and giving you colors that play across the spectrum. These are never rainbow colors. These are more interesting mixed ranges of colors, purples, just different strange little combinations of how the light might do it. So sunlight gives you all sorts of colors, and you get these really beautiful bubbles. But think about this. Where's that coming from? It's coming from quantum mechanics. Not only just quantum mechanics, it's coming from a form of quantum mechanics where you have to do some games, even with the concept of how a particle sees itself over time. So the photon as a particle is playing two roles at the same time. And experimentally, it has to have time to complete that. It has to have some temporal uncertainty that you would call it in quantum mechanics in order to see this color. Without that, you won't see any color. It's as simple as that. The color depends on the ability for the photon particle to get a little bit lost in time and look at reflections of itself. Conclusions. Let's wrap this up here. As I was just saying, soap bubbles are pretty because they depend on a level of, what would you say, some of the most fascinating but simple things that go on in the universe. This idea that there are amplitudes associated with particles, that these amplitudes turn, that these amplitudes are related to the total energy and mass of the particle. All very fundamental concepts of our universe. And the soap bubbles show that because they play games with these parameters, because they play games, little tiny games with time. But you can make those games larger and larger until it starts getting quite interesting. So Einstein thought photons are particles. People didn't agree. People still don't agree. I mean, we have, if you look, for example, the many worlds interpretation does the exact opposite. It says there are no particles. It says that everything is actually a wave. So those are essentially the absolute opposite ends of that spectrum. Then you have what's called pilot wave. That's a viewpoint that you have both a wave and a particle. And again, Feynman would not go there. Neither were the people in the MWI. They want to have one or the other. But what Feynman did that, as far as I know, no one else ever tried, was he said that, yeah, it's particles, but obviously it's not behaving like any particle we've ever seen. It has to behave in an extremely non-classical fashion that gives these different images of the same photon that then combine together using this simple idea of a little arrow that rotates in time and then rotates in different ways. And you add those together and you wind up getting some very good predictions. So when you do this, and this is something I'll get into more in the later lectures, but Feynman played enough games with classical time and location that he was very casual about saying that you don't get speed of light until you add a bunch of these probabilities together. So for Feynman, there's several places where he says point blank, that at small enough scales, the speed of light doesn't matter. And then it's only as you add them together and the probabilities together that you get an emergence of what we think of as classical time and classical space. When people talk about decoherence, they're talking about some related issues, that when things aren't interfering with each other enough, then you start winding up just, there's no way back. You can't do that. And Feynman talks about the same idea, but Feynman does it at a much more precise level of detail for two particles, electrons and photons, than anyone else. And he does some really interesting things with that. And I would argue that one of the reasons why Feynman was able to get a good level of calculation precision was precisely because of his emphasis on simplicity. You see it is so easy to get into this thing about saying, how can I make something sound really impressive, very complex, lots of integrals, lots of this. Yes, if you're calculating it, you need all that. Yes, that math is extremely important for getting the full calculational probabilities, descriptions. You have to have that. Feynman loved getting into that. He was always diving into different kinds of math, but he also never backed off from the idea that beneath that is simplicity. Somewhere down there deep, there's something going on that is just maybe as simple as a little clock dial running through space and giving you whatever you want. And with that, I will wrap up this part of my talk about the Feynman lectures.
I noticed George has a question earlier. He asked a more formal description might be vector area like Grassmann or Clifford. Just thinking one here.
The Clifford algebra and the Grassmann algebras absolutely are interesting and I think better ways to approach some of this. Feynman, I think, was respectful of some of those mathematics. I am very fond of some of the Clifford algebras. I think they do a nice job of saying that there's more going on here than meets the eye, and you get some interesting connections. The Grassmanns are a little more. They're more. He was notorious for being a bit more cryptic. And I think Clifford's work is kind of easier to understand. But if you never looked at a Clifford algebra, well, those are neat. They seem to capture some of these properties in a very nice way. And I'm trying
One
to
remarks, Terry, that our world, I don't know why it's more algebraic than metrics.
could you say that again?
In my opinion, I don't know why, but our world works more algebraically than just ordinary space with metrics and how we imagine three-dimensional space and time and etc. So, as you shown, all of this is more algebraic and mathematical than just our intuition and thinking how we see our world.
I think there's yeah, one of the things that to me is just marvelous, and you see it in QED, is Feynman's description about how simplicity emerges from the complexity of these interactions. He essentially loses all boundaries at the lowest levels, and yet from that he sees an emergence that looks very algebraic, much more simplistic, and really understandable. One example, and again, this is from slides that I'm not presenting today, but there's this interesting case of the Feynman diagrams. That when you look at the Feynman diagrams, they show an you can have a thing where you have an electron going through space, a photon hits it, the electron goes on for a little distance, and then it gives off a photon again, which you call, scattering the photon. One of the things that they tend not to emphasize to people when they learn that in physics is that both of those vertices, the one where you have the photon hitting the electron, is absorbed by the electron, and then the electron carries it and then comes back out, that vertex is physically impossible. It's what they call off shell. It has a combination of momentum and of mass and of energy that cannot happen in the classical world. It's impossible. It's off shell. But in that domain, it can happen. And this is, which is a marvelous thing about that, is that you have this very standard thing in Feynman diagrams, and people don't even realize that the interactions, the little vertices they show, cannot happen in the classical world. They're not possible. And yet you have simple algebraic type structures that emerge from that after you go through that. So it's a fascinating connection between them. Any other questions?
Maybe one thing, because this picture is very nice, but of course, this is trying to classical view of how we can understand these strange properties of lights. And for electrons, this book is, of course, not so deep like for photons, but QED is just a quantum field theory, so at normal physical level. So, what do you think about these kinds of theory to represent any kind of interaction? Because as I said, okay, this what you shown and how Feynman show it, it is just for pictures and to understand, okay, there is something strange, but we can imagine that this is vectors and this is phase. And if we look at that, we can realize a lot of experiments and a lot of imagination about how photons or light can work. Yes, but the true level is much deeper than that picture.
Yeah, I think it's interesting. Somebody in one of his lectures, I think it was the New Zealand lecture, somebody asked him, said, Dr. Feynman, do you think that your QED theory is the final theory that shows everything? And Feynman immediately says, no. He just, the bluntness with which he says it is remarkable. He just says, no, this is not. He says, this is a calculation, essentially a trick, a mathematical calculation trick that shows that certain simple assumptions lead to an unusual and unexpected level of calculational power. But he had no illusions about it being the final answer to how some of this works. And in fact, he was frustrated. There's interesting quotes. He always wanted to explain things to his dad, and he felt genuinely disappointed in himself that he was never able to fully explain what an electron is to his dad. He was disappointed that he was never able to explain the self-energy of an electron. So Feynman was keenly aware that his theory was not complete. The reason what I like most about it, though, is again, a bit of a personal bias in this. He stuck to the old concept that in simplicity lies calculational power. And I think he proved that pretty darn well. He said that if we do nothing more than this, look at how precisely I can calculate certain properties of the electron. Now, does that mean he calculates the whole universe? No, I'd say there's huge things missing. Quantum field theory, does it predict the entire universe? Good heavens, no, because it predicts that the universe will explode or collapse in an instant. So if your theory predicts, which most quantum field theories do, that the entire universe is going to explode in an instant, something needs to be done there. You can't just add an arbitrary constant, which is what they do right now for it, and say, yeah, we'll just cancel that out. So yeah, Feynman's theory was not a final theory. Quantum field theory is definitely not a final theory because it only explains locally. Locally does extremely well. Across cosmic spans of space, it does not do well, and also has difficulty handling just simple relationships of why the universe exists at all.
Yeah, but in that direction and this philosophy, you can say that all theories are kinds of approximation that do not describe everything. So
Yeah. Well, and I think, and that certainly was one of Feynman's adamant thesis. It shows up in his answers. Is when people would ask him about his own theory, he'd say no. Now, unfortunately, I think too often this is so tempting for every person in the world. I mean, whether in physics or not, is we all tend to want to say that whatever I have as a premise, that's the right premise, and then you start building everything around that premise. And Feynman did that. I mean, he said about particles, but he did it in a fashion in which he say, yeah, let's see if it actually works. And he got his to work a lot better even than probably he expected himself. But if you insist that whatever your premise is going to be the idea that explains everything, you're probably in trouble right there because always, always, always we have to go back to experimental observation. So you look at some of the supersymmetry theories as an example. I always can't help but bring up supersymmetry would explain a lot of things. There's just one problem. We've had decades of work that have shown not a single trace of supersymmetry being actually how the universe works. So you can always use that excuse and say, well, we just have to try harder, or you can acknowledge that probably that idea is not how it works, and then go on and look at something else. Sometimes we get too entrenched in whatever idea we think that's got to be it. That's got to be it. That's the only way it can work. And we want to be careful about that.
Terry, can you do a presentation on time crystals? I know Sebastian and Q Poland has done some interesting work in this area, but for people who are not physicists and scientists at that level, it would be great to have a presentation how you're presenting things, which is a little clearer for the non-expert, so to say.
That is a possibility for a future thing. I would have an initial reluctance to it because one thing I liked about doing Feynman is I have no problem being fully in sync with what's going on. I'm not sure I'm in sync with some of the interpretations of time crystals. Anytime someone talks about a time crystal that's driven by energy, I'm saying like, then that's not a time crystal. But yeah, that could be a possibility, but I would definitely have to give some different viewpoints. To me, the time crystal is when there's no energy input. There's no energy input. Yeah, sure. I mean, even here, I've just been talking about blurring time for 2 nanoseconds just using photons. So I would tend to lean to the idea that time crystals are probably more common than we think, but they're not quite what we think. And that some of the work here is interesting work, but calling it a time crystal, and I'm not the only one who's questioned that, calling it a time crystal, if it's being driven, is maybe not ideal. There is a YouTube physicist, and I'm sorry, I forget his name at the moment, but he has done a couple of excellent presentations on time crystals. And my apologies, I don't recall who he is at that, but there are some YouTube resources for that also. But we'll keep that in mind as a possible future talk. Other questions?
Can I ask something? I just, as a non-physicist, I just wonder that physics, unlike some other subjects like in engineering, physics appears to be more instrumental than ontology. Instrumental in terms of developing equations and so on, and mathematical descriptions rather than pure ontology. I just wonder, for instance, in this case of work by Professor Richard Feynman, if this work on the quantum electrodynamics had some practical applications in real engineering, or is just purely theoretical descriptions rather than engineering applications. So that's I wonder if you had any understanding of applications of his work on the quantum electrodynamics.
Quantum electrodynamics, I've never actually looked at where and how it might have impacted specific areas. It has certainly helped on the theory side in terms of understanding particles, and which of course was his goal in the first place. It also provides a basis for organizing the math and getting the math that is most definitely used quite commonly for any kind of optical phenomena. If you're trying to do optical computing, these issues are extremely relevant. If you're doing optical quantum computing, you would need to address some of these issues with that. And not sure if I can think of specific examples. That's something actually I'll try to look at in that. He's had other issues where he's brought up points. I remember he predicted quantum vortices that are he was just kind of casually looking at some other work, said, well, aren't you going to get vortex-like structures in this? And it turned out he was exactly right. I mean, under another set of circumstances, he could have got a Nobel Prize just for that prediction. But while Feynman was very interested in the everyday world, he recognized his work in QED as being more of trying to understand how the electrons work. And I don't think he put a really big emphasis on would that lead to a new technology. I would say that it can if you look at areas like quantum computing, that closer examination of some of Feynman's principles are still relevant for some issues of quantum computing. The current models that are used for quantum computing are more on the Deutsch mini world side. And as I mentioned before, Feynman was very much in the particle side, but with very interesting twists that no one had done before. And I would still think that his work is relevant for analyzing quantum computing issues. The Deutsch model, to be blunt about it, has not panned out well. It's been in play for decades, and people keep talking about error correction, but really what they're talking about is the fundamental limit of how much information you can get out of one photon. One photon can only carry a very small amount of information. So you can talk about it interacting with an infinite number of worlds, but if you need an infinite number of photons to see those infinite number of worlds, what did you gain? And this is the problem that's the deeper problem that's going in a lot of qubit strategies. So I think there would be interesting applications of it and focused application of Feynman type concepts on optical quantum computing.
Thank you. Yeah, it's because I was thinking, but well, I was trying to relate it with it when you talk about reflections of light, and I was thinking about refraction as well, because more recently, over the past few years, there's been some development with metamaterials with
Yes.
negative refraction.
Yes.
So the people have been developing this kind of technology for clocking invisibility, making things invisible. So playing with lights. I was wondering whether the work of Feynman had any application in this kind of studies of this new metamaterials. Yeah. But thank you for your answer.
Yeah, I don't think Feynman worked directly with metamaterials, but he did work with negative probabilities and had both scurrilous remarks, scurrilous things to say about them, but also very interested in them. And that's a domain of quantum mechanics where you get into this ambiguity about space and time. Bill, you had a question? Bill?
Yes, I just had to turn my audio on. I watched a video early this morning. I was so excited about this lecture. I got up in the middle of the night and I was just like, Feynman, Feynman, Feynman. I couldn't quit thinking about it. And I found this video on YouTube that talked about when Wheeler, who was Feynman's advisor, got him to organize a presentation at Princeton. And two of the people that showed up, two of the most famous people that showed up, were Einstein and Pauli. And what Feynman was lecturing about was the characteristics of electrons and how they the observability of what happens when they recoil.
Yes.
And so he had worked out the math, and it was all elegant. And I found out there was a subtle thing dropped into the description that said that one of the things that they always wanted to avoid was when the math leads to going to infinity, because it just kind of blows up. So he had worked out the math and delivered a very elegant lecture. Now, in his biography, surely you're joking, Mr. Feynman, he lamented that he appreciated Einstein's reaction, but he wished that he had tuned in. He said it was such heady stuff, like lecturing Einstein, that it was like he wasn't all there in the room. He was freaking out. And so, matter of fact, to set the stage, Einstein walked up to him and introduced himself just like he was a normal person at the very beginning. So that was very disarming for Feynman. He loved it. But at the end of the lecture, Pauli, who was known to be kind of an irascible jerk, said, "Well, this is all just a bunch of baloney. You don't know what you're talking about."
That is so Pauli, yes.
Yes. And so Pauli turns to Einstein, who's sitting next to him, and says, "Albert, don't you agree?" And so Dr. Einstein sat there for a second, and he goes, "No, I don't agree. I don't agree. I think Dr. Feynman has his ideas have some merit here. We need to explore this more." And so I invite people to go look for this presentation to Einstein. You'll learn a lot about physics and the hierarchy of what's accepted and what's not. It's very political when it gets to the top.
Pauli absolutely could be a jerk.
Yep.
And the example I point to is the first time someone came to the idea with the idea of electron spin to Pauli, which Pauli later got a Nobel Prize for. he browbeat the man so severely that the man backed off from it and refused to accept it, even after Pauli switched. He actually essentially just brutalized the guy to the point where he no longer believed his own thoughts. And that guy was the one who should have gotten the Nobel Prize. Instead, Pauli got it. So
Right.
Pauli is not one of my favorite people now, and that's an example of why I think that was just so. But it's also who Pauli was. His reaction was always to react as negatively as possible on the initial thing, and then he would consider it later. The trouble is that some people couldn't handle that, and in the case of the electron spin, the poor guy just couldn't. He couldn't accept it after that. Yeah, there's all sorts of interesting stories of Feynman interacting with other physicists, especially early on. And one of my statements I like to make about Feynman is one of the greatest physicists, I won't say the greatest, but probably one of the greatest physicists of the last half of the 1900s was Wheeler-Feynman. Not Feynman, not Wheeler. Wheeler-Feynman, because when you put those two together, you put Wheeler, who just would go Wheeler just go out there, he just explode to everything, just come up with the craziest idea possible. And Feynman would sit there and say, "No, no, hold on, hold on, hold on. You know, let's tie that down a little bit." But the combination of those two, I think they were more powerful as a team than either of them was later. Feynman kind of settled into continuing to do his Feynman diagrams for other particles, which was good work, but also it was more slugging along type stuff. Wheeler went out in some directions that are so wild that you read some of his stuff and it's just like, but what do you even say? You know, it's really wild stuff. But Wheeler, for instance, he called up Feynman one day, and this is recorded in some of the books, and he says, hey, Richard, I got an idea. There's only one electron in the universe. It goes forward in time as an electron, then backward in time as a positron, forward in time, and it does that an almost infinite number of times, and that's where the universe comes from. So the universe is half antimatter and half matter. And Feynman looked at it, and his own comment says, like, well, I couldn't agree with that idea, but I did like the kernel of it, which was that electrons could go backwards in time. And he took it and developed the full theory to QED, which I haven't gotten into those details. That's a fascinating part of it. Feynman really played games with time. He really did. And positron's a good example. Feynman had that electron going backwards in time on short distances. So he took Wheeler's idea and took it in a more pragmatic direction. And the result was just beautiful because that did produce an extremely predictive theory. But like I said, the combination of those two was marvelous. They had a respectful relationship with each other. They admired each other, but they had very different approaches, just very different approaches.
Sure. Terry, one other comment that I think people would find interesting. There was an American bluesman by the name of Paul Pena, who was actually born on an island off the coast of Africa, but fascinating man. And he went with some Feynman fanatics to the country that has the center of Asia. It's called Tuva, or some people call it Tannu Tuva. And the capital of Tannu Tuva is a place called Kizil, and they're noted for having triangular stamps. And so Feynman kind of considered himself an encyclopedia of everything, and he would bring it up in trivia discussions, saying, "Well, where is Kizil, and what is the only country in the world that has triangular stamps?" So with Ralph Layton, who was his protege and one of his best friends, they had planned a trip to Tuva, and it's all documented in Tuva or Bust. But what would happen was, between red tape and the fact that they were under the control of the Soviet Union, he just couldn't get over there before he died. And so the mission of Paul Pena and Ralph Layton's friends was to go over and, as a tribute to Feynman, go do this. And it turned out that Paul Pena was a genius. And he, through ham radio and shortwave radio, he had learned the Tuvan language and Russian. So
Wow.
so he was able to go over there. In that area of the world, Mongolians and Tuvans can do something.
Throat
And
singing.
throat singing, exactly.
Yes.
And
I was thinking that the whole time. Yes.
yes, and so I encourage people, if you really want to understand the final tribute to Richard Feynman, go look at Genghis Blues, because it's imperfect. It's a documentary, but he's Paul Pena goes off his meds. I mean, he's going nuts over there, in the last 1/4 of the film. But it's unbelievable that he goes over there and like wins the World Series. You know, he gets a world championship award for throat singing. So it's the final tribute of Richard Feynman. To, just go watch Genghis Blues and you'll get it.
I'll definitely see that. The story about them planning that trip, I'm familiar with that story. I haven't seen that video, but that was so sad that Feynman died. He had 2 forms of cancer at once. He had been a little too cavalier at the nuclear tests, and he had exposed himself more than most people. Of course, the risks were not well known at the time on that, but it did have a cost to him. So he lived until he was 69, but it definitely he paid a toll for it. He paid a cost for it. But yeah, that was such a. They wanted to visit that place, and nowadays Tuvan throat singing, for instance, you can find it on the internet. It's available, but it was such a marvelous and unusual thing, and it was such an interesting location, and it's so characteristic of Feynman that he wanted to see that. He wanted to go there. He wanted to experience that. He wanted to go with his friends. He was a very sociable person, and he wanted to see that. And of course, the sad thing is he did not. So I'll be sure to watch that. Thank you. Other questions?
Yes, quick comment there, Terry, about Richard Feynman. One comment about he was not only physicist, great physicist. He was an accomplished musician.
Yes.
Was a very good congas player.
Yes.
And also his work about the space shuttle, that failure of space shuttle was great.
The space shuttle incident is remember, as I mentioned, Feynman did not like people think that they had to respect it, that they had to have respect. It doesn't mean he didn't respect people. I mean, Feynman had enormous respect. If there's anyone that Feynman idolized, it was Dirac. And Dirac was kind of completely indifferent to Feynman, which is just unusual, because Feynman would try to talk to Dirac. Feynman was inspired by Dirac. Feynman got his key work from Dirac.
Yeah, but Paul Dirac was autistic.
But Dirac just seemed annoyed. There's this one-line paragraph that I'm pretty sure he's referring to Feynman, in which he grouses about people who have gone off into another direction and not paying attention to the Hamiltonian, and Dirac just dove totally into the Hamiltonian, disregarded Lagrangian. And he apparently was a snipe at Feynman. He said, why do you do that? Feynman got the idea from Dirac. It was an obscure paper by Dirac that gave him the entire idea of following the Lagrangian. And then for Dirac to just dismiss him. Dirac is a fascinating person. An extremely, as you said, it was autistic. It was a hard to describe person. His intuitions were impeccable, but his analogies sometimes were strange. The whole thing about the electron sea, there's so many reasons why you would never get away with proposing that idea in a physics class outside of that. And yet, even despite the straight, because you're filling space with charged particles, there's nothing else. And yet he captured the essence of semiconductors much later. with that model, and was able to express the positrons in it also. So Dirac's instincts and his ability to see things were just very difficult to explain and fascinating. And I'll put Einstein a little bit in that same category. Einstein was not a visual thinker. People think he's a visual thinker. That was Minkowski. Einstein was kind of a human physics emulator. And then with difficulty, he would try to express what he saw when he emulated physics inside of his head. Is the only way I've ever figured out to describe how Einstein did his thinking, because if you've never read an Einstein paper originally, it's really worth reading, because that man's mind is just amazing. Same for Dirac. You know, you need to read some of these people's original papers, not what people write about them. Read what they thought, read what they said, because when it was in their heads, it was different. It was not the same thing that developed after that, ever. So these original papers are always very insightful for understanding the range of thoughts I had to go through to come to some of these conclusions, and also quite baffling sometimes on how they actually came up with those final conclusions. Einstein's papers have certain areas where he just has kind of a leap of faith, and you kind of go like, I don't really understand how he got from there to there. And that includes for E equals mc squared, by the way, which for him was L. He never used E. He never used that equation in the paper, by the way. He used a different equation, didn't actually set it up as an equation even, but he did get that characterization. But how he got there was a little mysterious. So initial papers, reading them and trying to understand them is just so, I think, enlightening about some of these just amazing minds. Other questions? We may be nearing an end here then. Helen, are you there?
Yes, I'm here. Yeah, so far I don't see any questions. I see some comments that this is extremely good. This was interesting, and you have a way of keeping things light and serious simultaneously.
Okay.
Yeah, I got a lot of good feedback. Yeah.
Okay. Well, thank you, everybody. I guess we can go ahead and wrap it up. Thank you, everybody, for attending. I don't know when, but I certainly want to complete this, because this is just the tip of the iceberg. I mean, some of the really fun stuff is when you start getting into the interactions of the electrons and photons. So I definitely do want to do that in the future and talk more about Feynman's thinking on these kind of concepts. So thank you, everybody.
Goodbye. See you next week.